Friends, I welcome you again for this lecture on earthquake resistant design of foundations, and we are going through the pile foundations. That is the third module of this, and under the pile foundation we are discussing lateral load on piles. Continue with this lateral load on piles. What we have covered almost we have done for this topic, lateral loads on piles. Introduction, conventional method, elastic method using Winkler approach. Then we discussed solution for piles in cohesion-less soils, and then for piles in clay, including degradation of modulus of subgrade reaction. And in the last lecture we also discussed design procedure for piles. Today we are going to discuss some numerical example, where we are going to discuss 3 numerical examples. In one example, let us say the permissible deflection is given to you, and then you need to calculate and this the value of relative stiffness factor is not known to you, and so or you can say the diameter relative stiffness factor is not known because eta s is not given. So, we will, because permissible deflection is given for the given load. So, using that you can calculate the relative stiffness factor and then later find whatever deflections and moments need to be calculated, soil reaction. That is the first example. In the second example, for the given condition we are going to calculate the value of deflection with the depth, moment and shear and soil reaction. In the third case, which is typically a design problem where data is given to you and you need to calculate the diameter of the pile, and even though this is the tabular form and chart, but still today I am going to give you very good where you can use the closed form solution for this problem also. So, let us have the first problem. In the first problem it is like here, there is a pile, a single pile in sand. The pile is 10 meter long with head free to deflect and rotate acted upon a bilateral load of 3000 kg. That means the pile head is free, completely free, it is free against deflection as well as rotation. So, that means without any correction to the Reach and Matlock tables we can use directly for this. The EI, that is the flexural rigidity of the section, is given 3.5 into 10 to the power 10 in kilogram force per centimeter square. As you know, when we write the value of force like in kg, that means they should be read as a kilogram force. The pile undergoes a deflection of 12 mm, that is the deflection given, and this deflection is naturally, if nothing is written, that means this is the deflection at the pile head, that is at the top, which is normally the maximum deflection. If the piles in the group were restrained against rotation to the extent of 50% of fully restrained piles, determine the maximum bending moment and the soil reaction on the piles. In the first case there is no restriction. Using that data we need to calculate the value of deflection and bending moment when you restrain by 50%. So, basically in this case, and then plot the deflected shape of the pile, assume the width of the pile is 30 centimeter, that is the diameter basically, and the unit of the soil is given, neglect the group action, and phi is also given 30 degree. So, in this numerical example, what is the case? The data is given to you for the case when the pile head is free completely. Now, you need to determine the deflection when you fix the pile head against the rotation. So, let us see what happens to that. So, deflection given at the pile head is 12 mm. So, total deflection y is equal to y a plus y b, and because only the lateral load is acting on the pile head, no moment is acting. So, this term will be 0, this term is 0 for the case, the first case when you are keeping free. So, your deflection y becomes a y q g t cube and E I. The deflection y is maximum at the pile head, and at the pile head at z equal to 0, the value of a y from the table is this table. These tables are given by Reach and Matlock for cohesion-less soils, and you could see from this table that the value of a y is 2.435 for z equal to 0. So, this value is picked up from this table, and putting in this equation you put the value of a y, q g is given 3000 kg in the question, and T is not given, E I is given. So, using this relation you can calculate the value of T, which is relative stiffness factor. Otherwise, how we can calculate the value of T? T could be calculated E I divided by eta H over 1 over 5, but the value of eta H is not given here. So, the information of the soil modulus related to modulus reaction is not given. So, that is why we need to work the value of T from the here. So, anyway, once T is known, then in the next so here the value of T is here 179.15 centimeter. The value of T is given to you here, that so you calculate from this equation the value of T. Once T is calculated, then calculate the value of Z max, which is Ls by T, and Ls by T comes out to be 5.58, and this value being greater than 5, this is okay, this is acceptable, that means it can be treated as a long pile. So, first thing is that we need to apply the first check, that Ls by T should be greater than 5. Then now pile deflection for the case when you restrained the pile head 50% for the rotation. In that case, we need to, even you do not apply any moment, but still we need to use this equation Ay, this equation which we have discussed already in theory. What is this 0.5? This 0.5 is nothing but lambda. So, lambda is 0.5, and in this case, because all other things are known, now you can calculate the value of deflection y from this. And similarly, bending moment m can be also calculated from this equation, and soil reaction can also be calculated from this equation. Here you need to understand that the value of Ay, By, Am and Bm and Ap and Bp all are varying with the depth, they are not constant with the depth, and they varies according to this table, like Ay is varying with the depth, By is varying, then Am is varying, then Ap is varying, Bp is varying. So, all are varying with the depth, and once it is varying, then you can, then rest of the calculation we can do in the tabular form. So, the calculation is done in the tabular form as shown here. So, this is the case when you have the lambda equal to 0.5, not fully that means partially restrained. So, for this case what you could see, x is given from 0 to about 9 meter, and for the given value of x, z which is x by t is calculated here, which is 0.0, 0.2, 0.4. Then for these values of z, Ay, Am and Ap is taken from the chart. This same thing is here, and you could see back. So, from which table they have taken? Simply from these. So, Ay, Am, Ap, By, Bm, Bp. So, from using these table charts given by this Reach and Matlock, these values are pick up. Then the Cy is calculated as Ay minus 0.93 By. So, which is already here multiply by. So, simply this will be Cy will be Ay minus this column. This similarly the difference of these two Cm and difference of 2. Finally, we get the value of deflection using this relation, and deflection find out is, you could see at the deflection is maximum at the pile top, and this is coming out 0.828 centimeter, that is about 8 mm. But originally the deflection given was if you could see was 12 mm. So, that means when the pile head was free, for the same load was giving a deflection of 12 mm, but if I restrain the pile head, then the value of deflection reduced to 0.828 centimeter, that is 8 mm. So, about 2/3 deflection. So, which was expected. Then this is the maximum deflection. If I see for the moment, the value is 250 at the top, then decrease, and then you get the maximum value 255. While if I see for the soil reaction, the maximum value of soil reaction is coming at what you could have 13.28 at this point. However, here in this table that is not calculated separately, but there could be a column for Pa, where Pa is the allowable soil pressure, which can be calculated as 1 plus sin phi, 1 minus sin phi into gamma into x into b, which has been calculated later. So, this is here. So, you could see here that this Pa can be calculated from this relation. Phi is given 30 degree, gamma is 1.8, b is 30 centimeter, and x is nothing but Tz. So, putting the value of x equal to Tz. So, ultimately Pa you end up in this equation T into Z. where your z is varying with the depth and x equal to t z. So, you have just put the value and t is already known to you. So, the P A is also plotted. So, all the values calculated from this table here they had been plotted in this figure. So, deflection you could see deflection is maximum at the top and decreasing continuously and ultimately almost becomes 0 and negligible at the depth. As for moment, you have one side this side and then the moment start getting 0, it becomes 0 and then again increases. So, maximum value of moment is at some depth and similarly for soil reaction. But for soil reaction, allowable soil reaction is continuously increased with the depth. So, that means if I continue with this, so it will keep increasing while there is this Px keep varying with the depth like shown here. So, this was the case which is all these results are for the case when lambda equal to 0.5, that means if you restrain the pile head 50%. So, this was the one of the example. Now, let us discuss the another example where you have directly given the data, that means you have been given the value of modulus of subgrade reaction and then calculate. So, in this case a 15 meter long cylindrical RCC pile of diameter 600 mm is installed in a deposit of uniform sand in which modulus of subgrade reaction increases with depth to carry a lateral load of 100 kilonewton. So, the value of QZ is given 100 kilonewton and eta H modulus of subgrade reaction which was not known earlier is known in this example. Unit weight of soil is given, phi is given and for concrete E is 25 GPa. Assuming that the pile head is partially fixed with lambda equal to 0.5. So, in this example also lambda is 0.5 and known dimensional coefficient for laterally loaded piles obtained by the solution of differential equations has been given as here. Then first thing maximum lateral deflection along the pile depth, maximum bending stress along the pile depth show in tabular form, variation of soil reaction and permissible soil reaction with the depth up to a point until Px is greater than Pa. Actually here what you need to do in the first two cases, you need to find the deflection and bending stress along the depth and then find the maximum value, that is the objective to get the maximum value wherever it comes. So, let us see that this is the table which is same as before and this table need to be used along the depth. And what is the given data here? Given Ls, that is the maximum length of pile is 15 meter, D is 600 mm which is equal to 0.6 meter and E is 25 GPa and eta H is given here 10 to the power 7 Newton per meter cube. Gamma, phi and lambda are given here and QZ is 100 kilonewton. So, with the these are the all data given in this. So, what is the first thing we find? Ls by D, that is the slenderness ratio of the pile which is 25, that is ok. So, there is no problem, that is it is a cylinder pile, but still we need to check the value of Ls by T also, that should be greater than 5. Before that we need to calculate the value of T, relative stiffness factor, for that you require I and I is pi d 464. So, I is calculated here, then T relative stiffness factor is EI eta H to the power 1 by 5, you put all the numbers here and you, because E is given, I has been calculated, eta H is given. So, ultimately you get this value of relative stiffness factor 1.739 meter or roughly 1.74, approximately 1.74 meter. So, for this value of T, apply the check that Ls by T, Ls is given 15 meter and that comes out to 8.65, this is greater than 5. So, it is ok, that means you can use the solution which has been developed for the long piles. And for this solution Ls by T, we continue maximum lateral deflection and maximum lateral deflection here is calculated as Yx equal to Cy Qz T cube over Ei. So, what you have here Cy in this case is calculated from this relation is given here Ay minus lambda into 0.93 By, where lambda is 0.5. So, you put the value of lambda 0.5 and you get this factor 0.6465 and deflection will be maximum wherever, because in this case you see Cy is varying with the depth and Yx will be proportional to Cy because other factors are constant. So, as the Cy will be Yx will be maximum, wherever you have the value of Cy maximum. So, the calculation has been shown in the table, and you can see when z equal to 0, Ay and By is here, Cy is given here, and you could see that Ay, this factor Cy is continuously decreasing, and the maximum value is 1.680, which is at the top. So, along the pile depth the maximum value is 1.680 for Cy, and this will occur at z equal to 0, that means at pile head itself. So, the value of Cy will be maximum at z equal to 0, and for the Cy you calculate the Yx maximum, and the Yx maximum you get is 5.557 millimeter answer. So, this was asked. So, because in the question only the maximum value was asked rather than the variation along the depth. Here because as an engineer we are interested in the maximum value. So, this was the story about the deflection. Now, continue with this, the maximum bending stress. To calculate the maximum bending stress you will require bending moment first, and again the bending moment m is not constant, rather this is varying with the depth and according to Cm. So, m will be maximum wherever you have the Cm value maximum. So, you could see here that Am and Bm are given and the Cm is varying 0.465 and this is decreasing. However, then it becomes somewhere 0 and then again it keep increasing 407, 452, 470. So, maximum value is coming here, this is the maximum value. So, we will be interested in the maximum value here, which is occurring at z equal to 1.6. So, this value of Cm is used here in the calculation. Using this value of Cm and putting the value of Qg and T, then you get the maximum bending moment equal to 81.733. So, you could say roughly 81.73 kilonewton meter. And for this maximum bending moment you calculate the bending stress using this formula mx max divided by I moment of inertia and then d by 2. So, when you put all the numbers then you get this bending stress 3.8855 into 10 to the power 6 Newton per meter square, or you can say 3.855 kilonewton or you can say simply Newton per mm square, that is also typically. So, 10 to the power 6 will not be used, 10 Newton per mm square, that can also be said. Then next, variation of soil reaction, Px equal to can be calculated Cp Qg by T, and here again Px will vary with the Cp, but problem with the Cp, like even if it is maximum, that does not mean that you are safe, that is not the case. But what we need to make sure that ultimately your objective is that all the depth Px should be less than Pa, and mind it that both Px and Pa they vary with the depth. Not only the Px is varying, but your allowable values are also varying with the depth. So, let us calculate both Px and Pa. So, what is done in this slide, that Px is Cp Qg by T, where Cp is varying with the depth, and this is calculated at a particular, let us say that depth. So, you have this so this should be into Cp. So, this is some here, as Cp varies with the depth, soil reaction also varies. So, you put 100, so this should be one thing is missing here. So, you put all the numbers, this multiply by Cp, this should be multiplied by Cp. As Cp varies with the depth, soil reaction also varies. Allowable soil reaction Pa is given by this relation, where all the numbers when you put phi, gamma, b and x, only x is variable. So, this is varying with 13, so this varies, Pa is varies like this one. So, here Pa varies due to x, Px varies due to Cp. So, where x is nothing but Tz. So, when we have this ultimately Pa can be end up if you put in terms of x value in Tz. So, this is a function of z. So, now with the z, how Px and Pa is varying, it is shown in this table. So, z is varying from 0 to 0.9, Ap and Bp is given, and once Ap and Bp is known, then Cp can be calculated in this column, which is simply Ap minus 0.5. Once Cp is known, then the Px is 57.5 multiplied by Cp. So, this is calculated here, and the allowable Pa is calculated from this equation. So, here as the z varies, here as according to Cp varies, you could see at the top both Px and Pa are 0, but when z equal to 0.1, then Px is less than, Px is greater than Pa. it is negative, yeah. So, it is all right, that means it is this is negative, and but if you in absolute terms this is value is higher, and then again this higher values it is continue higher. So, P x is greater than, but after that because the P x is decreasing continuously in the terms of numbers and P a is continuously increasing. So, there is a point where if we compare only the numbers rather than sign, then this is greater. So, here P x is, so this is the case here, and other where, so this is the case here. So, up to this point P x is greater than P a, and that is not permissible. So, in that case we need to have this like that and then this was the case when we have given need to calculate the deflection moment and the soil reaction. Now, we continue with this numerical example and discuss the third case. In this case we need to design the pile, that we need to find the diameter of the pile. What is the problem? A cylindrical RCC pile of diameter 600 mm and length 18 meter is installed in a uniform sand deposit in which modulus of subgrade reaction is increasing with the depth. Assuming that pile head is fully free, that means lambda equal to 0, and using the Reach and Matlock theory find the lateral load the pile may safely carry. So, we need to get the here load is not given. So, what is the issue? The diameter of the pile is given, but the problem is load carrying capacity. So, QZ, so QZ is unknown. Give and this load need to be find out such a way that this is safely carried, it should be safely without applying all the checks. The permissible maximum lateral deflection in the pile is 10 mm and allowable bending stress is 10 Newton per mm square. Given that the unit modulus of subgrade reaction is given, also given, unit weight of soil gamma is given, phi is given, E is given for concrete, and the dimensionless coefficient for laterally loaded long piles are given in the chart, the table which we have already discussed. This table will be of course required in the calculation. So, what are given? The given data are listed here, d equal to 600 mm, ls 18 meter, fully free, allowable value of displacement, allowable value of bending stress, eta h, gamma, phi, E and all these things. So, we start our calculation and calculations are done here like this. First thing, always try to have fix the cell if data is given, diameter is given in this case. So, ls by d is comes out to be 30. So, it is quite enough. If LSD is coming more than 12, then this is okay, this cylinder pile, and then I is calculated because diameter is known. So, I is calculated as here and T is calculated as before 1.739 meter for this given diameter and the value of data. So, what you get when you Ls by D which comes out 10.35 which is more than 5. So, it is okay. So, 18 is the length of this. So, this is the first check you apply. Then again you calculate the value of EI is coming out to be this one, and for which we also use here. Then the safe load need to be calculated. Now, the safe load is that load where you do not exceed any check, that means the load up to which your deflections are within the permissible limit, your bending stress is within the permissible limit, and soil reaction at any depth along the pile is less than the allowable values. If you satisfy these conditions, then that is the load. Naturally, what you can do, you can keep increasing the load, you start from a small load and then keep increasing the load and keep checking and this one. So, it will be trial and error. Okay. So, you need to do a lot of exercise, or you can assume some load first and then check whether this, if it is safe, it is fine, then again decrease the load and find out the. So, in that case you need to do a lot of iterations. But from our experience, from our MTech class experience, what we have got it, that for this Reach and Matlock theory, even for not load is not given, still in that case you can find the answer in the closed form solution, provided you know that what are the checks you need to satisfy. You know you need to satisfy 3 checks. This check Ls by T is not dependent on the load. So, this is already clear. So, Ls by T is already satisfied. So, this is not the part of this. Now, you are left with 3 checks. One check is your deflection, and second check is your bending moment, and third check is that is bending stresses basically. Third one is soil reaction. But what we have observed that most of the time for the given loads, your deflection is within the permissible limits, your bending stress are permissible limit, but soil reactions get exceed than the allowable soil reaction. So, if you satisfy the soil reaction check first, and then after satisfying find the diameter, if diameter is not given, but this is given here, or you can find the load QG or MG whatever is the case, and once that load is calculated satisfying the soil reaction, then for that load if you check for deflection and bending moment, normally you get them in within the limits. So, the first in the one attempt normally what you can do, you can start for the case when the point at the depth where soil reaction is critical, and soil reaction how can be critical, that need to be calculated. What is the case here? In this case, first of all understand this pile head is fully free. In the question it is given that assuming the pile head is fully free, that means lambda equal to 0. That means when it is fully free, no moment is acting, we do not require this table. So, only this first part of the table will be required in this example. You do not need this coefficient B, that means this table is required only. Now, in this table for soil reaction AP is required, and you can see the value of AP are increasing like you know that if we do not talk about the here negative and positive is not an issue, rather than we for the soil reaction we are interested only in the its absolute value. So, what you could see the AP values are increasing with the depth, okay, and Z equal to, if I see in this table, then when Z equal to 0.9 you get 0.977 and then again it is decreasing. So, that means this will be the expected to be critical point for a soil reaction point of view, but this is not the case, and this can be proved that soil reaction case this will be not critical, rather it will be critical at the top, that is Z equal to. So, answer is this minus 0.227, this is the answer, this is not. And why this is the case here? Even 0.977 is more than 0.227, quite more than that, still the top values governs rather than 0.977. And what is the reason for this? You need to understand that though Px value will increase when the AP increases, however, your allowable value is also going to be increased. So, and that allowable value Pa is simply increased linearly with the depth. So, that means if I calculate the value of Pa in this column, next column I put here, the value of Pa which you get at this depth is going to be 9 times more than value at 0.1. So, that means if your check is satisfied at the Z equal to 0.1, it is going to, because if I compare 0.977 with 0.227, it is not 9 times, it is only 5 times, less than 5 times. So, it is here the SAF load can be found from the test data. The pile is critical in soil reaction, and for fully free case it occurs at Z equal to 0.1 where AP is 0.227. After that, though AP increases, but not proportional to depth, AP is maximum at Z equal to 0.9 where AP is 0.977 only if this would be this is less than 9 times of 0.227. So, still the critical case will be the Z equal to 0.1. So, with this way we can say that if you apply the check at Px equal to Pa at point Z equal to 0.1, find the load and that load will satisfy all the conditions. So, that and then you need to apply a check. So, to find that load we do our calculation assuming Px equal to Pa at Z equal to 0.1, which has been done in the next slide. For at Z equal to 0.1, for phi equal to 30 degree, sin phi is 0.5, as a result x Tz, and this so Px is AP QGT. So, you put the value of AP for Z equal to 0.1, put the value of T. So, ultimately you end up Px equal to this, while Pa is given from this relation which is ultimately at x equal to x equal to Tz, that is 0.1 into 1.739, and x and B what is 0.6, 0.6 is the diameter which is equal to B, and 18 is the value. So, you get the value of allowable load soil reaction is 5.634 kilonewton per meter, while Px is given from this relation. You equate these two values and you get the value of Qg equal to 43.175. So, if I take this QZ as it is, then there is no margin between Px and Pa, and we want Px should not be exactly equal to Pa, rather your Px should be less than Pa. So, your Q, you decrease the value of Qz. So, your final answer for Qz is 40 kilonewton, and for this 40 kilonewton you apply all the checks and see whether it is safe or not. For example, for this value of Qz, the maximum deflection calculated comes out to from this relation Ay, which is at the top when z equal to 0. So, you get 3.2 mm and allowable value is 10 mm. So, it is quite less. So, no problem. Then we calculate the maximum bending stress, and maximum bending moment comes out to be at z equal to 1.4, because you see in this table why this happens like this, why maximum at 1.4. You could see Ay is maximum at z equal to 0. So, we select this value, but for Am because this table will not be used for this case, this table will not be used, this is I cross it here, only we require this table, and in this table Am is increasing the coefficient, Kp is increasing, and this is maximum at 0.772 at z equal to, so this value we pick up. So, these values, and 0.772 is picked up from this table, and for this value you calculate here, yeah, maximum bending moment and then corresponding bending stress, and bending stress you obtain maximum coming 2.53, which is less than the permissible value of 10 Newton per mm. So, it is fine. Again we apply a check for the given load for Qz 40 kilonewton, Px and Pa. So, Px you find 5.22, while Pa is already calculated. So, Px is less than Pa. So, okay. So, all three checks are satisfied, and the Qz which we have calculated in one attempt 40 kilonewton is the answer. So, you can apply a load of 40 kilonewton on the pile without exceeding any the deflection or moment, bending stress or soil reaction. So, this is the case. I hope that all these three examples will help you to know that how we can analyze or how we can design a pile when it is subjected to lateral load, and most of the things as from the first references, and some thing are given also in the second reference, but the numerical examples which we have discussed, particularly second and third one, they has been coming from our classroom teaching through the MTech students. So, that is from our, and with this I thank you very much. So, almost we have covered most of the things on lateral load on piles, and with this lecture, and we are almost still in the middle of the pile foundation, because pile foundation is very important during the earthquake load. So, we will continue with pile foundations, and particularly we need to still discuss the dynamic analysis. So far we have not considered when you apply a load which is varying with the time. We have considered lateral load and the moment acting on the pile head. Okay, so in the next lecture we will talk about that, and so thank you very much for your kind attention. Thanks.